Welcome, friends. In the second part of my lecture series on carbocations, I have uploaded one video on carbocations mentioning the definition, what are carbocations, and second point which I took into consideration, stability of carbocations. In a very brief, I would like to repeat as usual, such type of species in which positively charged carbon is present. Carbon is positively charged. There are 6 electrons in the outermost orbit. Carbon is sp2 hybridized, planar in structure, and as it is highly electron deficient, it is Lewis acid, it attracts electrons towards itself. This is planar carbocation, or might be methyl or any other group, but this is the planar carbocation. And what type of hybridization? I did say earlier and today also sp2. Whenever sp2 hybrid carbon is there, one p orbital will remain vacant. Yes, because only two hybrid orbitals, two p orbitals are participating in hybridization. One orbital, p orbital as such, unhybrid will remain there. One p unhybrid orbital, in which they can accept two electrons. Sometimes, I will not take the name, I have seen a book, I took the name also, that book, that has put the positive charge inside the lobe. Please don't do it. Whenever you are talking about the orbital, to put the charge inside the lobe is a blunder. One of book I was looking, by mistake, they have put the charge inside the lobe. No, that will remain vacant. No charge is there. The charge is present on the carbon atom. Then I came to classification. We can classify carbocation primary, secondary, tertiary, such type of carbocations in which positive charge lies on 1 degree carbocation. They are primary carbocations. Simple methyl is a 1 degree. Ethyl, normal propyl, isobutyl, normal butyl, benzyl, allyl, all are primary. Secondary means positive carbon is attached to two carbon atom. That is secondary carbon. If positive charge carbon is attached to at least two carbon atom. The first member of the series I did say in my earlier lecture, isopropyl carbocation, or in another nomenclature, dimethyl carbocation. Secondary butyl carbocation means ethyl methyl carbocation or diethyl methyl carbocation. Whenever secondary carbon bears the positive charge, that carbocation is 2 degree. Diphenyl methyl, a good example of 2 degree secondary carbocation. Then I did describe 3 degree of tertiary, in which positive charge is present on the carbon, which is 3 degree, means which is attached to 3 other carbon. The first example of that category, tertiary butyl carbocation. Might be tertiary pentyl carbocation. Tertiary butyl in other nomenclature is trimethyl methyl carbocation. Tertiary pentyl is ethyl dimethyl methyl carbocation. Triphenyl methyl carbocation, 3 degree. These what I spoke just now, I described elaborately yesterday in 35 minutes. Then I came to the stability order. I very clearly mentioned there are 3 factors which influence the stability of carbocation. First is inductive effect, second is hyperconjugation, third is resonance. How can we explain the stability of carbocation by inductive effect? Inductive effect means the permanent displacement of all electron towards more electronegative atom. Permanent displacement of electron towards more electronegative atom or groups. I did say except alkyl and oxide, all are minus I. You remember hydroxide, chloride, fluoride, sulfonic, nitro, whatever. Amino even, you get methoxy, they are minus I. But alkyl group are plus I, means they repel the electron. So whenever alkyl groups are attached to carbon atom, they will repel the electron towards positive carbon. And as the magnitude of positive charge will decrease, stability increase. In my earlier lecture, I did say magnitude of charge is inversely proportional to stability. Suppose in 1 degree, I took ethyl carbocation. One methyl group is repelling the electron. Ethyl is much more stable than methyl. In normal propyl, one ethyl is repelling the electron towards positive carbon atom. Isopropyl, two methyl groups are repelling the electron towards positive carbon. In tertiary butyl, three methyl groups are repelling the electrons towards positive carbon atom. Once again, I would like to the structure. It is just repetition of earlier lecture. This is tertiary butyl. I am telling this is much more stable than CH3, CH, CH3. Right? This in turn is much more stable than ethyl carbocation. How can I explain through inductive effect? In this case, one methyl is repelling the electron towards positive carbon. In isopropyl, two methyl are replacing the electron towards more positive, right? In tertiary butyl, there are three alkyl group. Effect of three alkyl group will be more, and three alkyl group will make the magnitude much lesser than the ethyl carbocation. So according to inductive effect, tertiary butyl is most stable, then isopropyl, then ethyl. Second point, I took that into consideration, hyperconjugation. What is hyperconjugation? Such type of conjugation in which there is a conjugation between pi bond and hydrogen atom. Right? I did say that is also known as no bond resonance. I took number of examples earlier. In resonance, all atoms will unite to the species forming it. But in earlier lecture, that was quite clear. In tertiary carbocation, one of the hydrogen will come here and one hydrogen will remain as such, no bonding with the remaining species. So according to hyperconjugation also, here you have 9 plus 1 structures, right? In 6 plus 1 structures. In this case, I did say in hyperconjugation, many times I repeated in my earlier lecture, only alpha carbon. This is alpha, this is alpha. This is alpha, this is alpha. Suppose I put methyl, they will never participate in the hyperconjugation. No beta, only alpha carbon. So I can say tertiary butyl have 9 plus 1 structure. Isopropyl has 6 plus 1, 7 structures. Ethyl, 3 plus 1 structures. So according to inductive effect as well as hyperconjugation, I can say among three, tertiary butyl is the most stable, isopropyl is less stable than tertiary butyl, and ethyl is the least stable, both according to inductive effect and hyperconjugation. Now I will proceed further, which is the third effect which I mentioned yesterday. Beside these two effects, there are two effects which obviously participate for the stability of the carbocation, and third one I did say that is resonance. how we can explain the stability of some highly stable, even much more stable than tertiary butyl carbocation with the help of resonance, right? So third effect, I will say that is resonance. If resonance is there, that is a strong effect. Even I did say tertiary butyl has 9 structures. Which 9 structure? Hyperconjugative. Now I am taking the example. Yesterday I took the example CH2, CH, CH2. Right? CH2, CH, CH2. What is this? This is allylic or allyl carbocation. Allyl carbocation. Am I right? According to second nomenclature, I can say this is vinyl methyl carbocation. All are agreed with me? Why vinyl methyl? One hydrogen has been replaced by vinyl group. So you can say allyl carbocation or vinyl methyl carbocation. It has two resonating structure. In second resonating structure, pi bond will go here and positive charge will move here. This is CH2, CH, CH2. There are two resonating structure, undoubtedly. I can say there are two resonating structure in allyl carbocation or vinyl methyl carbocation according to second nomenclature. And due to two resonating structure, this is much more stable. And further, yesterday I did say inductive effect plus effect comes from the alkyl group. As the size of alkyl group increases, plus I effect also increases. The least will be of methyl, then ethyl, propyl, butyl. As the size of alkyl will increase, the plus I effect will also increase. Similarly, in this structure, you are looking two resonating structure. If some species have more than two resonating structure, that will be certainly more stable than allyl carbocation. Next example, very simple and very interesting. We all know that is benzyl carbocation C6H5 CH2. If you remove one hydrogen from toluene, that becomes benzyl carbocation. Benzyl carbocation undoubtedly much more stable than allyl carbocation. Reason? More resonating structure. You see, this is benzyl carbocation. In second resonating structure, this double bond will come here and positive charge will come to this ortho position. So I can say in second resonating structure, these two double bond will remain as such. This positive charge will come to here and this pi bond has come to form double bond. In third resonating structure, what will happen? This double bond will come to this place and positive charge will come to para position. So this double bond is as such, this has come here, this is positive charge. This is CH2. Now this carbon is not positive charge because tetravalent. In this carbon was trivalent, that was positively charged. In this structure, this positive charge is delocalizing inside the benzene ring. In next resonating structure, suppose this double bond will come here. I am sorry, it should be positive, not here. I am sorry. And this positive charge will go to here as a positive charge. So this is positive charge. This is CH2. 4 resonating structure we have seen. This is positive charge. In last resonating structure, what will happen? This positive charge will go again to this carbon atom and this pi bond will come again here. This is CS2 plus. So I can say there are 5 resonating structures in benzyl. And what could be the other name of benzyl? I am sorry. That could be, one is benzyl. We popularly say benzyl. That is phenyl methyl. Means one hydrogen of methyl has been replaced by phenyl. Phenyl methyl carbocations. Carbocation. How many resonating structure? 5. What is happening in resonance? In resonance, the positive charge which make the species highly unstable. I did say yesterday, as the delocalization of charge will increase, stability will increase. If the charge is more delocalized, more resonating structure will be possible, more stability will be there. In this case, this positive charge, this is bared by 3 plus 1, 4 carbon atom. See carefully, this is 1 carbon, this is 2nd carbon, this is 3rd carbon, this is 4th. This is again the same. So positive charge, instead of only 1, has bared by 4 carbon atom in 5 resonating structure. So benzyl carbocation is much more stable than allyl carbocation. And what is the reason? In allyl carbocation, 2 resonating structures were possible. In benzyl, 5 resonating structures are possible. We should go further. Means resonance is a great factor which can enhance the stability of carbocation. And what is the reason? Delocalization of positive charge. If positive charge will be localized to one atom only, the stability will be much less. If that positive charge can delocalize to other atom, the positive delocalization of positive charge will increase the stability. Earlier, I took the example of this compound. I put here CS2, that was benzyl. Suppose I replace one more hydrogen by another phenyl group. So this will become diphenyl methyl carbocation. Diphenyl methyl carbocation. Right, friends? When I took the example of benzyl just before, how many resonating structures were there? 5 resonating. 5 resonating structures in allyl carbocation. 2 resonating structures were there. In this case, how you can see, I will draw one structure which will make very much clear. I will keep this ring as such. First, I will show the delocalization of one ring. Obviously, the same process will be there. Suppose one bond come to this place, this positive charge will come to this place. So these 2 bonds will remain here. This positive charge will come to this place. And what will happen? This double bond is moved here. This will become double bonded. So this carbon, which was positive charge in diphenyl methyl, because due to delocalization of positive charge inside the benzene ring, it makes neutral. So I can say due to delocalization, stability will increase. How many resonating structure do you expect in this? This is 1. In second, the positive charge will come to this place, then to this place. 3 structure. Second, 1, 2, 3. I can say 6 plus 1, total 7 resonating structure. This is diphenyl methyl, right? How many resonating structure? 7 resonating structure. Quite clear. If I replace one more hydrogen by the phenyl group, right, that will become triphenyl methyl carbocation. This is what I am talking. Sorry, I will rectify it. This is nothing but triphenyl methyl carbocation. Or in simple language, I can say earlier I took benzyl C6H5CH2, only one hydrogen of methyl was replaced by the one phenyl group. In this, two hydrogen have been replaced by the phenyl group. In triphenyl methyl carbocation, three benzene rings are there. When three benzene rings are there, in this case, I have explained. Similarly, what will happen in this case? You will see this positive charge will come to this place, and this is formation of double bond. You can see how many resonating structures you can see in second. This one, this one, this one, this one, this one, then this one, this one, this one. I am looking 9 plus 1, total 10 resonating structure. I should write here in triphenyl methyl. How many? 9 plus 1 resonating structures. In benzyl, 5, diphenyl methyl 6 plus 1, 7. In triphenyl methyl, 9 plus 1. Just try to see, as the number of resonating structure will increase, delocalization of the positive charge will increase. If that charge can be delocalized with the maximum number of atoms, stability will increase. Certainly, I can say triphenyl methyl carbocation with 9 plus 1 resonating structure is the most stable. Then diphenyl methyl carbocation with 7 resonating structure. Then benzyl, which I took earlier, with 5 resonating structure, and that is more stable than allyl, which has only 2 resonating structure. So as the resonating structure increases, the stability increases. Allyl, yes, much more stable than tertiary, but among all these resonating, allyl is the least, then benzyl, then diphenyl methyl, then triphenyl methyl. Because as the number of resonating structure increases, delocalization of positive charge increases, stability increases, because delocalization makes the species always stable. If some charge is centered on one carbon, that is much less stable than the species in which charge delocalization is among 9 plus 1, 10. I hope you are quite clear. So I can say about the stability, 3 factors you have understood. We can explain the stability of carbocation with the help of inductive effect, that is a permanent displacement of electron towards more electronegative atom. Alkyl groups are always plus I group. As the number of alkyl group increases, plus I effect increases, stability of carbocation increases. Second, hyperconjugation, that is also known as no-bond resonance. Number of hyperconjugative structure increases, stability increases. Third, resonating. As the resonating structure number increases, stability increases. Least stable was allyl. Then more stable, benzyl. More than benzyl, diphenyl methyl. More than diphenyl methyl, triphenyl methyl. Now this is a very interesting example. Look to my statement also and this structure also. I'm sorry. Cycloheptatrinyl carbocation, cycloheptatrinyl carbocation, or tropylium carbocation. right? That is a 7-membered ring. You see this. What is this compound? How many atoms are there? 1, 2, 3, 4, 5, 6, 7. 7 carbon. This is cycloheptatrine. Cycloheptatrine. And we have to deal with cycloheptatrinyl carbocation, which is also known as tropylium carbocation. This is also known as tropyline. One point I will take before coming to the point. If I ask, this compound has 6 pi electrons, right? You are looking 2 plus 2, and we say whenever in cyclic system 6 pi electrons are in conjugation, that become aromatic compound. So like benzene, there are 6 pi electron, but unlike benzene, there are 7 carbon. So this is aromatic? No. This is not at all aromatic. This is non-aromatic. Non-aromatic compound. Why? Because for aromatic and anti-aromatic, I did say in my lectures on that topic, all the carbon must be sp2 hybridized to get the planar structure for the delocalization of pi electron. This is undoubtedly sp2 hybrid. This is sp2 hybrid. This is sp2 hybrid. This is sp2. This is 6 carbons are, I can say, sp2 hybrid. But this 7 carbon is sp3 hybrid. Because I have already shown 2 hydrogen tetravalent. Structure is not planar. 6 pi electrons are there, cyclic is there, alternate pi bonds are there. But this is not aromatic, this is non-aromatic due to presence of 1 sp3 hybrid carbon among 7 carbon atom. 6 are sp2 hybridized, all right. But the 7th carbon make nuisance due to the non-planarity of the tetrahedral carbon, the system become non-aromatic. Now I come to the point. This is just additional. Nowadays, if you see the news channel, you will find breaking bonus. Breaking bonus, they show the news of some their honest interest. So this was not a breaking bonus, or you can say breaking bonus. Now I come to the stability. Suppose this is cycloheptatine, undoubtedly non-aromatic. Non-aromatic का मतलब, what do you mean by non-aromatic? Such compounds, they are cyclic, having pi system of electron, but they don't have planar structure. Or I can say their stability is almost comparable with their open chain analogues. So this is almost as much stable as open chain analogues. Suppose this hydride ion goes minus H. Hydride ion, hydride ion is removed, right? This species is there. This hydrogen is there, I can show. But one hydrogen has gone with both these electrons as hydride ion. H minus means there are 2 electrons on hydrogen. This is formation of tropylium carbocation. Now you can see how many resonating structures you can say. This is 1, 2, 3, 4, 7 resonating structures are possible. First of all, this compound is aromatic or not? I did say this is non-aromatic, not aromatic, non-aromatic. This is very much aromatic compound. Why aromatic? There are 6 pi electrons. These 6 electrons were already sp2 hybrid. Now this is also sp2 hybrid. Because all the 7 carbons are sp2 hybrid, there is formation of carbocation which is trivalent planar. There is delocalization of pi electron, means system. I can say this tropylium carbocation, is very much aromatic. There are 6 pi electrons, 1 carbon having positive charge. There is delocalization of 3 pi bonds with the help of this positive charge. Total 7 resonating structure, very much aromatic. And I did say earlier, triphenyl methyl, if you remember. Triphenyl methyl carbocation. In triphenyl methyl, how many resonating structure were there? I did say 9 plus 1, 10 resonating structure. Each benzene ring will contribute 3 carbon positive charge, 3 plus 3 plus 3, 9 plus 1 original, 10 resonating structure. So how many resonating structures were there? 10 in triphenyl methyl. How many structures you can look in tropylium or cycloheptadynyl carbocation? I should write this name also. Okay, this is the cycloheptadynyl carbocation. Trinyl, that should be there. 7. Which is bigger? 10 or 7? Certainly 10 is bigger than 7. I did say earlier, allyl is the least stable among pi system. Then benzyl is more, diphenyl more, triphenyl more, because resonating structure were increasing. I did see. Here you are looking, if you compare triphenyl methyl carbocation with tropylium carbocation, tropylium has 7 resonating structure, triphenyl methyl has 10 resonating structure, but tropylium is much more stable. Tropylium carbocation is much more stable than triphenyl methyl. Means, what did I say earlier? The carbocation which has less resonating structure 7 than the 10 resonating structure triphenyl methyl is more stable. Means, what I give the statement earlier, that is not applying to this. If the number of resonating structure increases the stability of carbocation, triphenyl methyl should be more stable than tropylium. But the situation is reverse, and reverse I am telling much more stable. If I write the data, 10 raised to the power 11 times more stable. Very surprising, 10 raised to the power 11 times more stable. Means tropylium carbocation, which has 7 resonating structure, is 10 raised to the power 11 times more stable than triphenyl methyl carbocation, which has 10 resonating structure. Why this is reverse? What is the reason? The reason is that if you consider there were 3 phenyl rings, right? There were 3 phenyl rings, and phenyl rings always aromatic. But that carbocation you cannot say aromatic. Right? This is aromatic. First thing, this 6 pi system is aromatic. First reason, cycloheptadynyl aromatic. Triphenyl methyl, generally you look, there are 3 phenyl group. They can participate in the resonating structures, but the system like tropylium, that is not there. Second important structure, suppose there are 3 phenyl groups. Like this. Due to the presence of 3 phenyl group on a small carbon atom, carbon is a second period group member. If 3 bulky C6H5 will be there, the shape will not be perfectly planar. That will become propeller shaped. PROPELLAR. To understand propeller shaped, generally I was telling to my student, you took the exhaust fan either in washroom, kitchen or anywhere, you will see the difference between ceiling fan. There is a flat, three pankhudis are there. But in exhaust, you will find a little non-planarity in the pankhudi. Due to that non-planarity, because heavy three phenyl groups make on such small carbon that carbon can't tolerate the three heavy phenyl group, so structure become distorted, that not remain perfect planar, that become propeller shape. That's why, in spite of 10 resonating structure, triphenyl methyl is less stable than tropylium. This is perfectly planar, no doubt. Sometimes persons say, might be correct, I will not say, if three phenyl group on a small carbon is there, there might be steric hindrance. So second reason we can say, but first reason is that propeller shape, steric hindrance, three phenyl group will make so much steric hindrance that the nucleophile cannot attack. If the nucleophile cannot attack easily, obviously the stability will increase. So triphenyl methyl is less stable than tropylium. One reason is propeller shape, in spite of 10 resonating structure, not perfectly planar, propeller shape. Second, steric hindrance of three phenyl group, which make it a bit difficult to approach the nucleophile. Friends, I will come to some more example because I wish that stability should be discussed in a single part, not the fractional lecture. Earlier, that was a routine. Yeah, if you write tropylium carbocation, that is very much stable, 10 raised to the power 11 times more stable. Quality is that it is not affected by water and air. I am telling you, such carbocations, methyl carbocations, we cannot imagine the even intermediate formation. That's why I should say yesterday, theoretically I can say methyl, practically not possible. Methyl carbonate is so less stable, but tropylium is so stable that it is a orange color solid, not affected by water, and even other nucleophile not affected so rapidly, so highly stable. But there are some other carbocation also that I will discuss in stability. What is the name of this compound? Tricyclopropyl, tricyclopropyl methyl carbocations. Carbocation, sorry, not it. Means all the three hydrogen of methyl carbocation are replaced by this cyclopropyl. Another carbocation. That's a very good example. What is this compound? Cyclopropene. There are two pi electrons. It should be aromatic. Why? Because 4n plus 2, n is equal to 0, 2 pi electron. But this is not aromatic. This is non-aromatic. Non-aromatic. Why? Because this third carbon, these two are sp2 hybrid. This is sp3. And that makes the structure non-planar. So this compound could be aromatic and will be aromatic in future, but cyclopropene itself cannot be aromatic, that is non-aromatic, right? Suppose I remove again one hydride ion with two electrons from cyclopropene. So what is the compound I will get? One hydride ion is removed. This is cyclopropyl carbocation. I put like this three cyclopropyl group, right? Three cyclopropyl group. You see the difference. This is tricyclopropyl methyl carbocation. What will be this? Tricyclopropyl. That is species as such. There are three cyclopropyl attached. Tricyclopropyl, but this will become cyclopropynyl cation. Cyclopropynyl cation. Right? In this case, there were three propyl group on carbon itself. Here are three cyclopropyl group on cyclopropene carbocation. This system is also aromatic, right? I wish to know from my friends which is more stable, this is or this is. Please write in the comment box. If you will write, I will be much more glad. Undoubtedly, till what carbocation we have seen, tropylium is the most. I can say these two are higher stable than tropylium. But which is more stable? You have to write in comment box. If I will receive at least 20 comments, I will explain. Otherwise, the stability of carbocation will over here. If I will get 20 comments from students, I will be reply which is more stable and why more stable. So friends, in brief, the stability of carbocations can be explained with the help of inductive, hyperconjugation, resonance. Tetrahedrobutyl, isopropyl, ethyl. Certainly tetrahedrobutyl is much more stable due to 3-methyl group, which make electron repulsion towards positive carbon, decreases the magnitude of the positive charge. In hyperconjugation, tetrahedrobutyl, we see 9 plus 1 means that positive charge on carbon is bared by 9 hydrogen atom. Tetrahedrobutyl is much more than isopropyl, and isopropyl is much more stable than ethyl. Then I came to pi system. Allylic carbocation, which has 2 resonating structure, is more stable than tetrahedrobutyl carbocation. Benzyl carbocation with 5 resonating structure is more stable than allyl carbocation. The diphenyl methyl carbocation is certainly more stable than benzyl carbocation because benzyl was having 5 resonating structure, but diphenyl methyl carbocation has 7 resonating structure, and that is less stable than the most triphenyl methyl carbocation, which has 9 plus 1 resonating structure. But more than triphenyl methyl carbocation, certainly more than, much more, 10 raised to the power 11 times more, that is tropylium carbocation. That is an aromatic carbocation, perfectly planar in structure, but triphenyl methyl, due to presence of 3 bulky phenyl group on a small carbon atom, make the molecule from planarity towards non-planar. I will not say totally non-planar, towards non-planar. I took the beautiful example. You see the fan and you see the exhaust fan that become propeller shape. Or second reason, 3 phenyl group may create the steric hindrance. Approach of nucleophile is difficult, so obviously stability will increase. This reply, I need 20 comments in the comment box. Thank you very much. If you like, please like it, share, subscribe. Thank you very much.